So this is the continuity equation, and this explains one of the most fundamental principles of electromagnetism, especially the current, that the current is conserved. The amount of current entering a sphere is the same as the current leaving the sphere. And we can understand this. J is the current density, that is the divergence from the source. And rho is the charge density. And there's an elegant way of deriving this, and we'll get into it. First, P. In an enclosed cube, dV, the amount of charge in it, so dq is equals to the charge density rho times dV. And for a larger cube, I guess don't need a draw, but for a larger cube, we can integrate both sides, and we get that Q is equals the integral of rho dV. First part done. Now for the second part, the current. Imagine a sheet or a surface area that the current passes through. The key word is passing through. The current passes through this. So this is the charge density, and that is passing through a surface dA, which is oriented with a normal vector n. And the amount of current that is passes through, that is dI, equals the current density J times normal. This is the dot product of the current density and the orientation of the surface times dA. And why do we do the dot product, you may ask? Because we want to pick out the component of the current that gets passed through. So we use the dot product to get the component like that. And for a larger surface, we just integrate both sides. The integral here cancels out, so I is equal to the integral over the volume of the charge density dotted with the normal vector n times dA. Two part is done. Now we can go to deriving. If this is a sphere, the fundamental law tells us the amount of charge going in it, or the charge rate of change in respect of time. So d dt of q in will be equal to negative I. So the charge is leaving, so we put a negative sign and just plug everything in. d dt stays as q. We have found q. Integral over v of rho dv equals I minus the integral over v of j dotted with a normal vector. Just make some space over here of dA. Now move the derivative into the integral, and now this has two variables. So multivariable, we get partial derivatives. Negative. We use the Gauss's divergence theorem and get J times the divergence. Now this changes. This goes from dA to now dV because we use the Gauss's divergence theorem. Move this side. And then put the dV plus. So the integral vanishes for any value of volume we choose. So the integrand itself must be equal to 0 everywhere in this surface. Done. So this is the continuity equations or the conservation. This tells us that the amount of charge entering this sphere is the same as the charge exiting this sphere. So the current is conserved.